Alright, Assalamualaikum, a very good afternoon. So today we will be doing our project 2, which is 20%. And this is the PowerPoint slide that should open. And then let's see what should we do. Alright, so the project that we're doing is front bumper crash analysis. And if you look at the title, it's a story about a stationary automotive bumper which is to be analyzed during impact with the pole. So the pole weighs 1,000 kilogram. It has a diameter of 254 millimeter, and the current speed that we're doing the impact is about 29 kilometer per hour. So the bumper is made with this material, which is cold roll automotive steel sheets, or B410LA, and it has all these properties lah, which is the thickness is 2 millimeter, elastic modulus 210 GPa, Poisson ratio of about 0.3, and a yield stress of 433. So the second material is the crash box. So the crash box is made with cold roll automotive steel sheet B260LYD. So it has the same properties except for the yield stress lah. The yield stress is about 344 megapascal. So this is the configuration. And let's take a look at the material properties lah. So you've got both materials, B410 and B260. These are the data lah under experimental. However, we are going to be using elastic, perfectly plastic material lah for simplicity. So in the first study, we're going to study how does it perform after impact. So all the bumper thickness is about 2 millimeter. So we have to plot a few things lah. Let's find out what happens after 100 milliseconds. So plot your results of stress, deformation, kinetic energy dissipation, and also reaction force. And in the second study, we need to study what happens if you vary the thickness lah. So you want to study the kinetic energy dissipation. Alright, so let's download the geometry, which is the CAD. Open it up and then download the whole folder. And let's unzip the CAD. Right click, 7-zip, and extract here. So this is the CAD. Open it up. And then you're gonna see the assembly file lah. So open up the assembly file. This one, assembly 1. So let's check the geometry. So this is what the geometry looks like. You've got a pole here, and then you've got the bumper beam. If you look at the bumper beam, it's actually made with, it's actually shell material. If you look here, it doesn't have any thickness lah. You have to set the thickness inside your finite element analysis. So in order to proceed, we will be doing Ansys lah. So if you want to export your geometry to Ansys, you need to first of all file, save as, into step file. Save as into step file. So, but before we do that, we need to modify something lah. Number one, which is this pole. So I can right click and then open up the pole. So this pole is actually solid lah. So in order to do explicit analysis, you have to choose either all geometry must be shell, or all geometry must be solid lah. So in this case, we are going for solid. No, we're going for shell. So we have to delete certain surfaces lah. Number one, this you have to go to here, go to plus surfaces, and then click delete face, and then delete this one, and also the bottom surface lah, and then click OK. So now this has become also shell. So if you regenerate and then you return to your assembly, this has been changed. Rebuild the assembly, yes. So if you look at the geometry, everything will now be in shell mode lah. It's no longer solid. So when your geometry is like this, you click on something wrong here. Coincident on the pole. This fine. It doesn't matter. This one, since you are going to export anyway your file, so this one doesn't matter lah. Just hit file, save as. Maybe put your file at desktop, and then change this format to step. So you can give it a name lah. Bumper crash pole maybe. Make sure the format is step, STP or STEP. So once you've done that, so let's go and fire up your Ansys workbench. So everything in SolidWorks, you can now file, save all. This can be deleted. Delete this one. So there's no more error. I can regenerate. And this one I can save all. So I don't have to open up my SolidWorks anymore. I can turn it off. Now let's wait for Ansys to run. So one Ansys workbench has been opened. You need to look for something called static structural. So take this out. Static structural. And then you've got static structural, and then you've got engineering data lah. So you can double click engineering data. So this will come out lah. So under engineering data, you will have every single thing with regards to material. So you can click filter engineering data, or you can click engineering data sources lah, this button. If you click it again, it will go to your material lah. If you click it again, it goes to some sort of database that you can choose. For example, if I scroll down, I can go for general material, additive manufacturing material. If I go down here, everything will be written here. I can still go down and look for explicit materials. If I hit explicit material, the choices which is available for explicit will come out at the bottom. Yeah, you've got aluminium 2024. This one is explicit material. And then you can browse down. There's a lot of materials that you can use in your analysis. So let's go back to your engineering data sources. This is a toggle. You click, you go to database. You click again, you will go to your material that you want to create lah. So in this case, we are going to create a new material lah. So the material that we're going to use is this one. Cold roll steel sheet B410LA. So this is the material name lah. Should I put the whole thing or just put this nickname? This one lah. B410LA. Copy. So I can click here and then paste. So I've got B410LA. However, it has a question mark, so it requires some properties. So the property that I need is this one lah, the first one. Top here you've got physical properties lah, all this density, you don't need to take one by one lah. Take under linear elastic, click on this one, isotropic elasticity. You can double click. So once you double click, the material property will go down here. So you have to fill in the yellow color box. So this material B410LA, let's take a look. The elastic modulus is 210 GPa. So change the unit to GPa 210. Next will be the Poisson ratio, which is 0.3. So this is done. However, I would like to add a few more things lah under B410LA ni. The one that I need to add is something called plasticity. So I have to go down to here. Isotropic elasticity has been done. Next, I need to look for something called plasticity. So this one. So I can take this one called bilinear isotropic hardening. Bilinear isotropic hardening. So this is the material that I want lah. The material properties. So I can double click. So it will add here. So this is bilinear isotropic hardening. So it's under plastic. So I can key in my yield strength. So yield strength I can put in the unit as megapascal. And the yield strength is actually 433 lah. 433. Double click here. Key in 433. So tangent modulus is actually, you can key in also if you want. However, if you don't want, we just maintain it as elastic perfectly plastics lah. So tangent modulus is some sort of like this lah. If I open up new slide, so let's draw something. So currently the modulus, so bilinear meaning it has two linearity lah. One like this, the other one is like this. So this is called bilinear lah. This is your linear region. This is called your plasticity region. So this is what it means by this one. Tangent modulus. You need to find out what is the value of y over x to get tangent modulus. So find out lah this one how much megapascal. So you get the value, which is y over x. So if you want to key in tangent modulus, you can key in. Otherwise, we can just assume it to be 0 lah. So it goes like that, and then it goes flat. So something like this, the tangent modulus, which is y over x, is equivalent to 0 lah. 0 over x, so equals 0. So there's no tangent modulus lah. So currently we are simplifying the analysis by putting 0 tangent modulus. Okay, let's go here. So tangent modulus, I key in 0. So I've got one material created, B410LA. So you want to create another material. Another material is called B2610LYD. So this is the new material. So you just have to go to B410, you right click, and then hit duplicate. Just click duplicate, and then this thing you can rename lah. Rename to B2610LYD. So the rest of the material is the same. You only need to change this one lah, the yield stress, which is 344. To change this one to 344. So this is the material lah. So I've got first material, which is the bumper, and second material, which is the crash box. So this is done. I can file and save lah. save as a project, maybe at the desktop. Bumper crash. So my engineering data has been completed. Now I go to project. I can actually click X. I can hit X. So the project is still here. If I double click engineering data, the same thing will come out. So I've got two material, which is this one and this one. Structural steel is actually default. Structural steel, there's a lot of material here. You even have things like SN curve, strain life parameters. Does it have plasticity? No, it doesn't have any plasticity. It only has isotropic elasticity. There's no plastic here. However, our material, we have under plasticity, active table, which is plastic, bilinear isotropic hardening. So this one I can click X, I can go back to project, and then I can go to geometry. So under geometry, I hit right click, and then click import geometry, and I'm going to browse to the desktop, which has the step file which I have created. So this is checked. And then I can go to model, I can double click model. And wait for it to load. So this is the workbench, mechanical workbench for Ansys. This is the user interface. Alright, so you've got a few things You've got a bumper, and then you've got crash box, and then you've got another crash box, and you've got a pole. So bumper, if you want to rename it, you can go right click here and then hit rename bumper. And then I've got crash box. I can right click, I can rename box left. No, box right. Crash box right. And then this one is right click, rename crash underscore box underscore left. And then I've got a pole pole is the tiang rename. So I've got 4 things which has been exported here So the geometry is not continuous, it's different So you got a bumper, crash box right, crash box left, and then pole. So one thing you can see here, at the bumper you need to key in the thickness So let's say the thickness is actually 2 millimeters, so you hit 2 and then click enter. So this thing will be changed to check mark Next, your crash box also change to 2 millimeter. Crash box left also change to 2 millimeter. And finally the pole. Pole you can put whatever maybe 2 millimeter also. So for pole, if you click bumper, this thing, the stiffness behavior is flexible. See here, stiffness behavior flexible. Crash box R is actually flexible also. Crash box L is also flexible. However, if you go to pole, we are not interested in the pole behavior We consider the pole is stiff. So if you click pole, change this one. Stiffness behavior change to rigid, so it does not deform under any load. So this is the pole. So the pole has some weight to it. Let's say the pole weighs about 1,000 kilogram. Since the pole is under impact, the car is actually stationary. We are reversing the speed. So this pole, if you want to put the weight, you can right click lah. Right click here, insert point mass or distributed mass. Doesn't matter lah because the whole thing is rigid. So point mass is good. Point mass, and then if you click this one, only one surface is attached. So the best way is to change this one lah. Oh no, you have to click control and then click another surface. So you've got two surfaces, and then hit apply, and then you have to put the mass lah. The mass is actually 1,000 kilogram. So this is done. So you've got a pole that weighs 1,000 kilogram. So now let's configure the crash behavior lah. Number one, you can look at connection. Under connection, there is contact. So currently it detects this thing is to be very close together, although it's actually not that close lah. If you look it properly, zoom, so there is actually a gap lah, so it's actually not in contact. So I can hit zoom to fit. It's actually not in contact with each other. So this contact I have to go right click and I have to delete lah. Delete the contact. However, I want to add something called manual contact region. Hold on. Connection, insert. Oh, this is static structure. So static structure, there's nothing yet lah. Oh, this is wrong lah. We are not actually doing static structural. We have to go for dynamics. How do I exchange this one? So quite an error. Static structural, no, actually we're not doing static structural. We are actually doing dynamic explicit. Never mind, we learned something. Let's finish it off. We cannot do anything with static structural. Can I replace this one? Insert, no, I don't think I can do anything with it. What I can do is that I can take out another one lah, which is explicit dynamics. Take this out, and then this geometry I can directly copy here, link it. Yeah, I can actually link it. If I double click this one, this will be another project. Engineering data also I want to copy. So since we're doing explicit dynamics actually, however, by using Workbench, you can share things. So you don't have to do engineering data again because it has already been created. However, if you start from the beginning, you can start doing explicit dynamics alone lah. Because static structural is just doing basic stress analysis lah. Currently, we're doing crash analysis lah. So don't worry, everything can be linked. So now if I double click this one, engineering data, what does it look like? It should have the materials that you have. B410 dengan B260 LYD. However, this is still static structural. We want to look at this one. Double click model. So static structure, you can turn it off. Click X. Now let's wait for this to load. Double click. It's not working. Fresh the project, bumper crash. Nearing data, it's not working. It's not link. B410, why? Oh, density is missing. No wonder. Okay. B260, you have to put the density lah. The density will be... Oh, we don't have density here. It's actually 7,800 lah. Go to here, 7800, and then click here, 7800 also. So now everything is linked lah. Because you need density in order to do dynamic explicit analysis. So I can turn this off. Now everything is checked. If I can click model again lah. Hopefully it works. Okay, so now we are doing dynamic explicit. Yeah, same thing, explicit dynamics. So it becomes handy lah, this workbench. You can link a lot of things. So sometimes people they tend to do component system. For example, I can go to where? Component, custom. No, actually I can click this one. I can hit geometry, make it standalone. Because later I can link with any other project that I want. Maybe I want to put engineering data as a standalone also can. Yeah, I can even do like that. I can even link geometry. I can link here. Sort of like a graph. What graph? Like a chart. I can even link my DC engineering data. I can even link here. Make it standalone, so everything can be linked lah. So you can build your complexity lah in your modeling. The following component need attention before. Okay, some error just now because we didn't put density. When you're doing explicit analysis, you need density lah. So obviously I don't need this one lah. Maybe something you want to do this. This is standalone. You can do any analysis you want. So this one I don't need lah actually. Delete. So this is linked together. So we're not going to be doing any static structure lah. Static structure is just basic stress analysis. We're doing impact, so this is under explicit dynamics lah. Just now I double click model. This has come out. So let's rename it again. I have to rename the geometry again. Bumper. Can I rename here? Cannot lah. I have to right click and rename again. Bumper, and then you've got crash box, right, and then rename crash. I don't know, can I use space? Crash box left. Yeah, I can use space. This one is polar. Rename. POLE pole. So everything is in tanda soal, question mark. So you need to put in values where you have the yellow value. This one is 2 millimeter. Then it becomes check mark. Also 2 millimeter. Also 2 millimeter. And also another 2 millimeter. So everything, the modeling is okay now. Okay, next our material. If you click on bumper, what is the material? It's actually structural steel, right? So this one you have to change lah. Change this one to B410LA. And then your crash box, right? Change structural steel, change to B260 LYD. Crash box on the left, also change material, change to B260 LYD. Pole can be structural steel, doesn't matter lah. This is actually rigid. So again, stiffness behavior, change this one to rigid. And then the pole also, you want to insert a point mass of 1,000 kilogram. Yellow color. Select the surface and then control another surface. This one, so two surfaces lah. Click apply. So two faces. It has point mass does not point mass. Okay, point mass is okay. Behavior is rigid lah. Change to rigid. Behavior of the point mass change to rigid, and then behavior of the pole change to rigid lah. So we're done on the geometry. So next we can do mesh. So the mesh has a kilat here. You gotta right click and then click generate mesh. So this is the default mesh lah. Default mesh density that the program is giving you. So if you want to make it the thickness has been modeled in the element. You can see the thickness 2 millimeter. So if you want to add to make it much better sizing, you have to go to mesh, insert sizing. So maybe I want to change this one to body, change this one, and then control this one, and then finally this one. Click apply. 3 bodies, element size is currently 28, right? 28, right? Maybe I want to change to 20, and then I can right click and update. So it will mesh with a finer sizing lah. You can see a finer sizing. So this is how you control the mesh density. So if you look at statistics here, you've got 2,422 elements lah. So this is very, very small lah. This is good enough lah. Okay, so now let's go to explicit dynamics. You want to add velocity to it, so you go to initial condition, expand this one. There is no pre-stress. You have to right click and then insert something called velocity. So the velocity you are applying to this body, which is the pole. Click apply. The pole is traveling vector. Change vector to change the component. Change this one to component. So the component is in the Z direction lah. So Z has to travel 29 km per hour. So 29,000 millimeter per second lah. 29 kilometer. Right? Is it 29 kilometer per hour? Oh, we gotta change lah. It's not exactly. Oh, this one is millimeter per second lah. You have to change properly lah. Convert. Kilometer to millimeter per second. Kilometer per hour. Let's convert it properly lah. 29 kilometer per hour. It's actually around 8,000 lah. 8,056. So let's change this one. 8056 millimeter per second. Okay, so this is the velocity in the Z direction. So it's going to hit the bumper lah. Next thing we have is something called analysis setting. N time is actually 100 millisecond lah, or 0.1. 100 millisecond is actually 0.1 second lah. Okay. Next will be the solution. You can right click, insert deformation, and then click total. Right click, insert the stress, von Mises, and right click, insert stress tool, no, probe. So you want to probe things like energy, and also you want to insert something called force reaction lah. Force reaction at the boundary condition. I don't have a boundary condition created yet lah. So I have to create boundary condition. So go to B5, explicit dynamics, insert, maybe fixed support lah. Fixed support at this region lah. Change this one to edge. So you got 1, 2, 3, 4. And then another one. 4, 5, 6, 7, 8. So I've got 8 edges lah. So make sure you got 8 edges. This is fixed support. So now I can change lah this one. Force reaction, you will have fixed support. So this is the location that you will search for the fixed support force reaction lah. So I've got a fixed support, and I've got to create a velocity. That is done. So now I have to define the connection. If you go under connection here, they will have contacts. Where is the contact region? Again, it's actually trying to show contact region between the two. Is it under contact? Not in the initial stage. Let's try not to remove this. And let's look at body interaction. So body interaction is where it will detect different bodies lah. And then it will run and run accordingly. I don't think there's anything else but that's how you build a model lah. You start simple and then you try to run. So I should save by now lah. Save project. So in order to run it, I can just go to Explicit Dynamics V5 and then click Solve. So if there is any error, we can capture the error. So it's solving at 5%, 6%. So it's taking some time to solve. Should I pause? Stop. Pause recording. Okay, I'm gonna pause. And then we will continue. Alright, so we're back. So this is what it looks like lah. You can click total deformation and then click play. And then you're gonna see problems lah. So the object moves. If you take a look at the side, the pole moves and then turns a bit. So this is not the behavior that we want lah. So the pole needs to be moving in a flat direction. And then another thing that we notice, the beam is not actually attached to the crash box. So we need to rectify two things lah. So we can stop. Number one, we can take a look at the velocity change lah. Currently it's moving forward, and then x component 0 millimeter per second. Okay, this is okay. I think we need to add right click, insert displacement lah. We want to control the displacement. So the displacement, we want to control the pole. So click body, click the pole, click apply. This body we want to control it not to move in the x direction 0, and also y direction also 0. So it's not moving in the x direction and y direction. However, it can freely travel in the z direction lah. So this is the behavior that we want lah. Displacement. Next thing we need to control is that we need to attach the crash box to the bumper. So in order to do this, we gotta go to connection, insert, I suppose connection group code. Try connection group. This one to this one. No, not connection group. Delete this one. Let's find out. Is it contact? Contact, create. No. Body interaction can connection, insert. I think this one code, manual contact region. Let's try. Connection, insert, manual contact region. So contact is this bumper. Click apply. Target is this crash box. Control another crash box. Click apply. So make sure one body with two bodies. So if you've got a bumper with multiple bodies, the type has to be this one lah, which is bonded. So when you click bonded, it will be glued together lah. It is joined together. So this is the thing that we want lah. So since we have corrected these two things, I can go to solution B6 again and then click solve again. So it's currently running again lah. So I'm gonna pause the recording and gonna continue. OBS pause recording. Okay, so this is the next analysis after we have rectified. Hopefully it has is okay. You can go to total deformation and then click play, and then currently it's attached lah, attached to the bumper lah. The deformation, this is total deformation. So let's look at stress. So if you look at the stress value, there are two data lah. One is the 431, 433, the stress, which is the maximum. It goes linear and then it goes plasticity lah, flat line. And then if you click on energy, you can take a look at all the energy involved lah. For example, internal energy, plastic work. Let me turn off a few things. If you click this one, it will turn off. Click this one, what energy is this? Hourglass, energy probe contact, and then finally energy probe total lah. So this is the two main energy lah. One is the kinetic energy. So kinetic energy, it's half mv squared lah, from a very high value, and then it drops lah. So the kinetic energy is being slowed down by the bumper. So the energy from the kinetic energy has been converted to plastic work lah. which is the blue color one. So this one you can right click and then export to text file lah. Or right click and then you can double click click this one and then hit Control A, not Control A, Control C. Okay, number one, this one lah, you need time, Control C. So let's go to desktop, create a new Excel file, and then you're going to paste here. So this is the time. So now let's copy kinetic energy. So Control C. This is paste. So this is kinetic energy lah. Kinetic. So this one, insert. Let's put kinetic energy here. Kinetic energy. Converge everything. So this one is actually 2 millimeter lah. KE 2 mm. So if you highlight these two things and then click insert, where is insert? Go to charts, scatter, and click this one. Kinetic energy. So this is the kinetic energy which is being slowed down lah after 0.1 millisecond. This one can format axis. Number scientific change lah. Change to just number. So this is the kinetic energy. The unit is in millijoule lah. Click plus here. You can click axis title lah. Axis title. This one is in. So this is kinetic energy in millijoule. This is time in seconds lah. So this is the value for 2 millimeter. Insert. This is time. Okay lah. Okay, so let's do more lah. By doing more, meaning you need to change the this one. Change the so plot the stress. You can find the stress, plot deformation, kinetic energy dissipation, and also reaction force. Where is the reaction force? Go back to here. Is there a reaction force? Yeah, force reaction. So this is the reaction force lah. Force reactions in the Z direction lah is mainly total. X direction, nothing lah. Y direction, nothing also. So why do we have two values? Force reaction Z and also total. Okay, so you can this is vector lah. This is the magnitude lah. If you look at the vector, it will be in negative value. If you look at total, it will be in positive value lah. So this is the reaction force for both lah. Both of the supports. This one is currently traveling like that. 20 frames ah. Can I slow it down to 5 frames? Oh, it's not smooth 30 frames. 2 second auto. Oh, meaning if I go 10 second, it will run slower lah. There's a vector here. So this is what's happening to the bumper. Okay, now let's change the thickness. So bumper, just change the thickness lah. For example, I change to what was it, 1 millimeter. If I change to 1 millimeter, click here, change to 1 millimeter, change also lah the crash box to 1 millimeter. This one also 1 millimeter. Change to 1 millimeter. So everything is 1 millimeter lah. Bumper 1 millimeter, 1 mm, crash box 1 mm, crash box left 1 mm. Pole, it doesn't matter, just leave it there, 2 mm. So actually if you take a look at the statistics, it has a property, right? It has a weight lah. The weight is about 3 kilo lah. So you got 1003 kilo lah. So now if I run it again, right click here, solve it again, then let's wait a few minutes lah. Alright, so we are done. This is running at 1 millimeter, so we can, let's take a look at the deformation. You apply, so it's traveling much more severe lah, deformation, I think. Much more severe. So let's take a look at the energy. Let's look at energy and look at kinetic energy. Control C, Control V. How about the time? Is it still the same? Click time, Control C, Control V. So the time increment is the same lah. So this one can be neglected. So this is, so I gotta change this one lah. KE 2 mm, Control C, Control V. So now I change this one to 1 mm. Delete this one. And then copy this one, Control C, Control V. So this one is actually 1 millimeter lah. So I can click Control and then just drag. It will automatically copy lah. So if I click this one, I can just change lah this one. Move this thing to here, so it's going to be 2 mm. So if I want to find the combined behavior, I just Control C this graph and then paste here. So this one, I think I gotta put data label no legend okay, put legend. Gotta put legend lah. Legend, put it at the bottom or top. Okay lah, top. So I've got two data. So 1 mm, 2 mm. Next, let's take a look at 3 millimeter. What happens? So 3 millimeter. So you have to run again lah. Go to here, change 3 things. Change to 3 mm. Does it change everything? Yeah, it does. It changes every single thing to 3 mm. Doesn't change the material, it does change the thickness lah. So now I can run it again, click right click, solve. Alright, so we are done. So let's take a look at the deformation. This is, I think, about 3 millimeter. Not as severe. However, our data, we are always looking at energy probe and look at kinetic energy, right? So Control C, click this one, Control C, and Control V. So this one, you can change this one to here. So becomes 3 millimeter lah. Now I can Control C here and then paste here. Make sure I add in the data label. No, legend. Legend at the top top also can. So this one I can delete. So you can do it this way, or you can, I think there's a way to do this. It's quite intelligent now, Excel. You can highlight the whole thing, insert X. Yeah, it's very intelligent. You can even do that. This one is done manually. This one is, yeah, same thing. Kinetic energy, same thing lah. So this is 1 millimeter, this is 2 millimeter, this is 3 millimeter. So kinetic energy is very important, right? How do we calculate kinetic energy? You still remember? Let's go to draw, red color. Kinetic energy is actually half rho v squared. It's not half rho v squared lah. Wrong. Control Z. Half m v squared. So this is how we calculate kinetic energy lah. So half, the mass I think is about 1003 kilogram. And then the velocity is in meter per second, okay? 29 divided by 3.6. You will get lah how many you can put here actually. 29 divided by 3.6. Now if I squared, what is the value that I will get? I need to get an eraser. Where is my eraser? This is the value. Unit is in joule lah. You should get this value 3.267, but this one is in millijoule lah. This one is millijoule. So which one is better? This one is something that you have to find out lah. So kinetic energy is energy when something is moving. If the kinetic energy dissipates early, meaning the thing is stopping and slowing down lah. So if it's like 1 millimeter, it actually still has kinetic energy at after 0.1 seconds, meaning the pole is actually still traveling lah. So it's actually not stopping lah. So 3 mm, the pole can stop lah at 0.1 second. So do one more lah. So you have to do one more, which is 4 millimeter. Okay, so this is how you do it. How to do impact analysis on Ansys, in this case a beam lah. Alright.